Hey guys, so this week we are going to be looking at slopes and intercepts as outcome variables in latent growth curve models. We last week looked at just modeling change across time. The truth is we can examine different types of variables that affect that change across time and also affect mean levels via the intercept. So we have these two basic types of covariates in these latent growth curve models. We have what are called time invariant covariates, and these are covariates that don't change across time. For example, for the most part, biological sex is a time invariant covariate. Not for the most part. Biological sex doesn't change. For the most part, gender doesn't change. So, of course, we've seen that gender tends to be more fluid than we initially thought. But there are things that are relatively fixed that will not change across time. One of the things that I do in my research is looking at the effect of an intervention, which doesn't change across time. You do it one time and then you follow people across time. And so you can compare trajectories across time as a function of the intervention. That's an example of a time invariant covariate. Then we have time varying covariates, and these are things that do change across time. So, for example, we might be modeling alcohol use across time and alcohol problems across time, and maybe we just decide that we want to control for the effect of use on problems and model problems over time. We could do this by simply regressing use onto problems at each time point, or we could do this by using a dual process latent growth curve model. The dual process latent growth curve model was your assignment from this past week, and this is what a dual process latent growth curve model looks like. We have two different slopes, a slope here and a slope here, and you can, like, we've got these intercepts predicting these different slopes, and you can do that if you want. Oftentimes these intercepts and slopes are correlated is all. And then you see that this one has a correlation between slope 1 and slope 2. You can also have slope 1 predicting slope 2. There's a number of different ways to look at this, and really it comes down to your theory and why you're testing a certain thing. So when we look at this data set here, we actually have both, right? We have time invariant covariates at the time of the intervention, so their age, immigrant status, parent education, whether they're an active coper or not. And then we have stress at and social support at wave 1, stress and social support at wave 2, stress and social support at wave 3, and depression at wave 1, depression at wave 2, depression at wave 3. And so we've got these time invariant covariates predicting the slope and the intercept of depression in these cases, and it wouldn't make any sense to put them down here. It makes more sense to add them right here. In fact, if you were to regress these variables onto each one of these, it would affect this, and it would affect this as well, but you wouldn't actually get the overall effects on these two outcomes as a function of these. In the end, what we're going to talk about is that each one of these, when they predict a slope, what they're really doing is telling you if there is significant variance in that slope, if the slope varies based on age. If age is a significant predictor of slope, that means that there are different slopes at different ages. Similarly, if we, for example, use like immigrant status, yes or no, and predict the intercept, and we have a significant effect, then all that means is it's basically a t-test looking at depressive symptoms, average depressive symptoms by immigrant status. If immigrant status significantly predicts depressive symptoms, then you can say that depressive symptoms change across time differently for immigrants and non-immigrants. So here we have the time varying covariates. These are covariates that are assessed at the same time as each one of these waves, and then the time invariant covariates, which are assessed a single time point and are used to predict the intercept and slope. All right, so what I was just saying a little bit ago is that the time invariant covariates wind up if they wind up predicting some significant portion of variance in a random slope or random intercept, then they explain why a slope varies. We've run into this before, right? This is what happens when we do a regression analysis with a moderator variable. We're saying that the slope of some variable x on predicting y is different at levels of m. And that's really what we're talking about here. If a time invariant covariate significantly predicts a slope, that means that that slope is varies as a function of that covariate. In other words, that is an interaction effect, right? When you think about the way that you plug in your effects, you have an effect of x, an effect of m, an effect of xm, and then you need your intercept. In this case, the intercept winds up being the average level of I, right? In a like the mean effect of I, the effect of m on your outcome in a simple slopes analysis for a latent. Let me do this. The I would be just the mean level of intercept. The m variable would actually, let's say we're using immigrant status, would be the effect of immigrant status on depressive symptoms. That's your effect of m on y. The x would be your average slope across time, and x times m would be the effect of immigrant status on slope. So we can plug this in to a simple slopes calculator and get the change in slope as a function of your time invariant covariate the same way that we would do with any other type of moderation analysis. And we'll do this in class this week. So when we look at this, we can see we have these different BMI trajectories, and we have a bunch of different types of trajectories, right? And so here we see that the trajectories vary whether you are male versus whether you are female across time. And so it's just a moderation of your slope of BMI across time as a function of male versus female. This is another study that I did using time invariant moderation of slopes. So we did an intervention, and before the intervention, we assessed like norm frequency and norm discrepancy, and then we used those to predict the slope of PBS use across time. And then we used that slope to predict the slope of alcohol use across time. And so what we found was that the pre-intervention PBS norms, like how much they think people are using PBS, predicted the change across time. So you can see our slope was 0.005. There wasn't a whole lot of slope, but for people with higher PBS norms, we saw a steeper slope across time. Similarly, if your slope tends to go up for PBS use, your alcohol use slope tends to go down. We see a negative association here, right? And overall across time, not that this matters, but we saw a decline in alcohol use slope across time. But so this is a moderation analysis that's looking at the moderating effects of an intervention on PBS use and how that then affects alcohol use. And so you can see if we can change this slope, then we can change alcohol use even more. And that's the purpose of time invariant and time variant covariances on latent growth curve models. This is what we're going to work through this week. It's exciting, it's fun stuff, and it is it starts to fill in some of the gaps about why I emphasize moderation so much in ARM 2 and the first part of ARM 3. But this then is what those slopes look like across time. So at low levels of norms, we see this. At mean levels, we see something like this, and at high levels, we see something like this. And note that this is the same sort of Excel file that you guys have been using to plot these simple slopes for the past several weeks and or months if you've been with me for a while. So anyway, we're going to do some of this in class. I think that this is going to be fun. I will see you guys later this week.